In the subject of mechanics of solids, we will eventually be dealing with combined loading problems. For this example, we will be using a U-shaped piece of beam, maybe a C-clamp in real life.
We just cut this out of 2-inch thick carpet foam, put a little cardboard strip on each end just to kind of secure it a little more. The vertical lines are 1 centimeter each apart, and the horizontal line is the geometric center of this lower portion here.
The main thing that we want to understand about combined loadings is that when you have a force here and a loading on your object, you can really break that combined loading down into the force here as though it were applied in a purely compressive way on the lower part of the beam, and then also the resultant moment that you get from the moment arm from this force, which really just looks like a moment also applied here at the edge of the beam.
If I apply a simple moment here on the ends, you can see that the neutral axis is about where we have that center line drawn here, meaning the hash marks don't get closer or further away from them than when there was no stress added. Here's a simplified model in SolidWorks of our beam with just that bending moment applied. And you can see that blue line down the center is the exact center of that beam. And our neutral axis lines up nicely with that. If I apply a simple moment, but then I add tension, so I pull on the edges, you see that hash marks are getting further away from each other. So now that neutral axis has migrated. So here's the simple loading, and if I add tension, the neutral axis is now lower than it was before. Here's that same SolidWorks model with bending moment and tension applied. We'll see the exact same thing if we now apply this simple force, but on the arms. Here's a SolidWorks depiction of this model. You can see some distortions on the edges, but what we're really concerned with is that middle portion there that is displaying that behavior of the neutral axis and how it's now below the geometric center.
Here we can see another depiction of the breakdown of a combined loading into its constituent linear and bending moment stresses. We can represent that mathematically as the total stress as a function of x being the tension stress or the compressive stress and the bending stress. We can break those out into the tensile or compressive stress being force over area and the bending stress being the moment times the location divided by the moment of inertia. Breaking that out and representing things in terms of this force P, we have force over area plus force times length, that's the moment, and x over the moment of inertia. Now let's go ahead and solve for the location of the moment of the neutral axis, x. We solve for that by setting the total stress equal to x, which is of course the location of the neutral axis. Solving, we find that force falls out of the equation completely, so we know that the magnitude of the force does not matter at all in determining the location of the neutral axis, whether it be right in the middle or below. Now, solving for the location of the neutral axis, we find that it can be represented as negative moment of inertia over area times length. Looking at this in terms of A, B, and L, we see that the location of the neutral axis can be represented as negative 1/12 AB cubed, that's the moment of inertia, A times B, the area, and then of course length. Now let's go ahead and simplify. We can cancel an AB here and an AB here, and we end up with negative 1/12 B squared over L. So that tells us the location of the neutral axis. We can see that it is only a function of this dimension here, B, and the length of the moment arm, L. A does not play in, and the force does not play in. Now, let's go ahead and throw some numbers in here from the demos we looked at earlier. So we tried to increase the moment of inertia as much as possible while not increasing the area or the length more than necessary. So we have a very large B value coming from our moment of inertia, but a relatively small length value, which put together, these two things lead us to an expected 0.47 inches movement of the neutral axis. We see it's negative because we expect the neutral axis to move downward on the part. After conducting the test, we see that we measure 0.27 inches, so about half. Now that's not surprising given the fact that the demo is made of foam and does not translate forces the way that other materials might, but still a pretty good estimate. Here's how we know that the neutral axis will move downwards in this analysis. As we said before, we can break this system apart into compression from stress and compression from bending. Here's a good way to visualize that. We have the compressive stress, and we have the compression and tension from bending with the neutral axis right in the middle. Put those together, you have more compression on top because the compression adds, the tension does not, resulting in more compression than tension, and that forces the neutral axis downwards. Although we won't show it here, you can prove for yourself that if you reverse from compressive to tensile loads, you still move the neutral axis downwards and instead have extra tension on top and a smaller amount of compression on bottom.
Thanks for watching your video. I hope you learned something about foam.